Chapter 9 of Interactive Statistics Methods talks about normality. So everything we've been doing up to this point has been building actively towards this chapter. This is the foundation, this is the core of the classical or frequentist statistical methodology. We're talking about, when we come to normality, we're talking all about the Gaussian distribution, otherwise known as the normal curve. That bell-shaped curve where large amounts of scores from a given distribution cluster around the group mean. In the normal curve, the mean, the mode, and the median are all considered to be equal. So the mean, the most frequently occurring score, the mode, and the median, which is the middle score, are all equal. And that is one of the powerful principles that we want you to learn in this book and in the course that you're taking, in which this book is used, and understanding how that curve is formulated and what it really means. So chapter 9 begins talking about a type of variable. What is a variable? It's anything that varies. A score, anything that's ratio data, has a true zero point and can vary and can be calculated. The types of random variables, continuous variables, and probability distributions are tied in. Now, probability distributions are what functionally help us to begin to build normality, understanding that a group of scores have certain tendencies, have certain things that allow them, when they're grouped and clustered together, and if that same type of experimental mechanism, a test or causal comparative experimental design, or looking at relationships, if that particular experiment is replicated, repeated over time, you're going to get similarities and see similarities in a distribution of scores. Of course, all of this is from a sample extracted from a population so that we can infer back to that population and find out if our hypothesis, our general research question, is tenable, if it has enough support for it to be accepted, or alternatively, if it's false, it's null, and it can be rejected. So the beginning talks about probability distributions and your understanding of how probability plays into building the indefinite integral, which is going to be transformed into normality. So this is where integration comes in, and mostly what we want you to do is just read this and understand that it's a layered by layered process as you're moving down to understand how the normal curve is formulated. So we know that our integral allows us to graph things on a normal curve, and as we go further, when we look at things in terms of x, y, and z in a Cartesian coordinate graph, we begin to see, and that's that same three-dimensional representation of that same curve and where the area is. You see the gray areas, and that's described in the book. And there's a lot in this particular chapter in terms of the normal curve that begins to aid you in understanding, because as this piece transforms and we begin to see normality and how all of this wraps itself around itself and lends itself to giving you a visual representation of what's actually going on. So you can see that, you even see the integral sign in there as you're looking at this graph. Okay? Now, as we begin to look at algebraically, as we begin to transform and look at distributions, we begin to recognize that if you replicate these things over time, there is a normality, there is an average, there is a standard that can be produced, especially if you have a given hypothetical distribution with a mean of 0 and a standard deviation of 1. And that begins to formulate and build our actual normal curve. And what are the properties of this Gaussian integral, this normal curve? How does it begin to transform? How do we go from the indefinite integral when we're looking at things in terms of infinity, and how does it begin to become a Gaussian integral and begin to take shape of the normal curve? And that's what these subsequent mathematics and illustrations begin to show you as you take the area of the square root of pi and you begin to look functionally at this dark line and how it begins to shape itself. You begin to see the transformation from a probability distribution in which we have a mean of 0, standard deviation of 1, into a normal distribution in which any distribution can fit that data as long as you have the mean and the standard distribution of that data. Of course, the standard deviation being the square root of the variance, how things vary. And what we begin to notice is it's bell-shaped because scores tend to cluster around the mean. The further they are away from the mean, it means that they're exceptional. When you have all parameters ideal in whatever that situation may be. Okay? So we're back to kurtosis. Now we have a graph that looks at and placing different types of curves in terms of kurtosis overlapping one another and looking at what they look like. From the standard normal curve in this very back to one that is mesokurtic and elliptokurtic, and you're looking at how values cluster more towards the mean and have less extreme values, and how they spread up to 3 to 4 standard deviations plus or minus away from that actual mean score. Population mean mu being here in the middle with the mean of 0 and a standard deviation of 1. It's beginning to shape what that normal curve is going to look like. And lastly, we come to our ideal normal curve. See if I can get this inside of our frame here. With a mean of 0 and a standard deviation of 1, 2, 3, and 4. And their percentages. All of this represents 100% of all the scores within a given distribution. But they're going to be spread this way if you have that mean, standard deviation, and the variance. So three-dimensionally, the normal curve looks like this. It's bell-shaped with extreme values, and it's spread out, going out. And our variance shows you where our mean would be idealistically where that block is and running right down the center, and how scores cluster around that mean. If you look at it from the side, you can even see the shape formulating of the normal curve. So what happens is when we take the standard deviation, we literally slice this bell curve in half and turn it on its side so that it looks like thus. And 1 standard deviation, 2, 3, and then on. This last line comes very close to that ideal line in which this rests, never quite touching it, but continuing on positively for infinity or negatively towards infinity. And as you read further and further in the book, you'll see how this formulation, how it developed from our previous chapter, chapter on measures of center, and 7, and then 8 when we talk about probability, and now 9, the formulation of the standard normal curve, where we have a mean of 0 and a standard deviation of 1. So as we move further and further out, and we actually have the calculation for what this actually looks like when you actually calculate it and you put it all together. This is the actual calculation for using the function f of x for the Gaussian distribution, where f of x is here, ideal line, and along our x-axis we have our standard deviations, along our y-axis we have our height of an ideal given distribution. Now, probability, in terms of probability, how does this break down? Between -1 and +1 standard deviations of the curve, you have, because at the mean splitting it, you have 50% of the scores here, 50% of the scores here. Most of them cluster around the mean. So if you add this 34.13% here, you have 68% of the scores are between -1 standard deviations and +1 standard deviations of the mean. They're all clustered in here. You're going to find the vast majority. The further out that you go, this probability breaks down. So you can see idealistically where you are. Now when you're actually given a standard normal test, you're able to see how these probabilities break down. So I want to show you here percentages of where the scores fall. It's a great chart here. Your standard deviations are here. Cumulative percentages, 50%, so you're going up from 0, the starting point, all the way up to 99, all the way up towards infinity, 100% of the distribution. Your percentiles, where you are, 50%, you're at the mean. Okay, where you are at 98% +2, or down to less than 5% at -2, and where the vast majorities of the scores fall. So when you're given an actual test, you're tested against everyone who takes that test at the same time. So when they say you're in the 98th percentile, you're actually 2 standard deviations away from where the average score of the test of all the persons who took that scored test at that time. That's really what that means, okay? Literally, that's the meaning of that. So here we're able to see where our z-scores are and t-scores, and more on that a little bit later when you start to actually score tests. There, once again, our f of x is, of course, y, and there is our Gaussian curve equation, which creates our normal curve. And that formula is broken down, and you can see exactly where things fall, where the shaded area means, and things of that nature. So the understanding of normality is the beginning of the understanding of how scores group and cluster and making inferential or inferences back to from the sample data that was calculated and that you're driving your research from back to that population. Now z-scores deal with a ideal distribution with a mean of 0 and a standard deviation of 1. And it begins to put everything on the normal curve in terms of respect of those scores. So when you look at 100% of an entire distribution, you know 50% is here. If you start from 0, you're going up to get 99%, but we know that 68% cluster within in here and 98% are in here. Anything down here was not very good, and anything up here is exceptional and very good. So this gives you a better idea of what normality is and how the normal distribution works. And then we actually have a calculated z table of z statistics. So when you begin to look at a score such as an outlier, when we gave the example of I believe in one of my courses I gave the example of a salary range for the University of Virginia when Ralph Sampson was there and went to the NBA, and how it pulled scores in a direction. We refer to that as a skew, and you have an example of that with these skewed distributions. And you talked about that earlier when we looked at the shape of distributions much earlier in the text in this particular book, where we talked about things being pulled in a direction. But this shows you where the mode, the mean, and the median are, since we're now talking about normality and how the shape of a distribution can be completely changed. The normal curve is the average and what you expect to see, and how things can be pulled when you have an outlier in a positive direction because of an extremely high score, or in a negative direction because of an extremely low score. And when you have those, the better indicator is not the mean, because the mean is going to go in the direction of the numbers. The median, the middle score, is a better indicator of what's really going on with those scores. And it falls again in the middle between those two. So where in the normal curve the three of those are equal, the mean is pulled and the median pulled in the direction of that skew. But the median is a better way to look at those scores. So then we talk and we end with looking at scores that have two means, bimodal, different types of data, and what data distributions can commonly look like. And we end the chapter looking at random sampling and minimal sample sizes and things of that, and beginning to talk about the population parameters, because now that you have an understanding of normality in the normal curve, we can begin to start analyzing the types of tests we want to use within our research design, and then be able to acquire that data and begin to put together a normal curve. So here's the mean, 52, the standard deviation is 12, and as you add up +1, +2, +3 gives you that entire score. -1, -2, -3, again 68% will be between 40 and 64, which is +1 standard deviation here, -1 standard deviation here. Most of them will be within this range, and then 98% at -2 or +2 between 28 and 76 when the mean is 52 and the standard deviation is 12. And that in a nutshell gives you normality and how it works. There's different graphs in here which shows your percentiles where they would fall. So if you were exactly in that last distribution and you scored in the time of this test of 64, this doesn't seem to be a good score, but you're actually in the 84th percentile. So where each of these fall is an exact percentile of that distribution. So as you pay attention to the graphs and read sequentially all about the chapter, it provides great graphs to explain to you normality in a normal curve, how a z-score and a t-score work. When you're going to reduce things down and get a sample score and find out where they fall on a z-score of that ideal population, you have a better indicator of where things fall. So if you read carefully through chapter 9, you'll have a better understanding of normality and the normal curve.